Get started. Okay, so this is the process control course, right?
Yes.
Okay, good. We meet Monday, Wednesday, Friday, 10:40 to 11:30, and I have an open door office hours policy, so you can drop in anytime that you want. If you have any questions regarding this course. But if you want to make an appointment by email, you are welcome to do that. But anytime without having an appointment, you can drop in as well. I go by the nickname Kumar. I've got a very long name. For sure, Nandakumar is my full name. But feel free to call me Kumar. And my office number is 210 in this building. The textbook that we are going to follow is the one that is written by Professor Nandakumar, who has been teaching this course at LSU before. I'm new to LSU. I just joined last fall. So I'm teaching it this term. This is a common requirement that I have. I expect individual effort in every assigned work, exams, and a pledge like this, and every work that you submit is expected. I don't know how many of you, I think a number of you have actually logged into Moodle already. I noticed that. I will put all my lecture notes on Moodle before the class so that you can print it out and bring it if you so choose. And that way you just have to listen to me. You don't have to take extensive notes. If you want to add on to it, that's fine. I also am experimenting with a technology where I record everything that happens on the screen, also the voice, so that at the end of the lecture, I will have a complete recorded lecture on Moodle also, if you want to refresh for any reason. Okay, so we'll see how much you use it. Of course, when you have 6 other courses, you may not have time to listen to the whole lecture, but there may be sections that you may doze off in the class, and you may have to listen to it again. Right? So you'll see, and I would like your feedback on how you find that. It doesn't take a lot of extra effort for me, just plug in the mic, and that's why I come a little bit earlier, and then it should be fairly transparent to us. Now, the assessment rules, I expect to have about 8 assignments in this course, and the assignments will be worth about 30%. There will be 2 midterm exams. I have fixed the date already for them. I will be very hesitant to change unless you have a very good reason. One is February 22nd, the other one is March 29th. Those will be in class, about 15 minutes, so they will be worth 30% each. And then the final exam is scheduled by the university, 2 hours, and that will be worth about 40%. And in assignment, I would recommend that you work individually, and that's how you find out where you have problems. And if you have problems, you are welcome to discuss with your friends or drop in and discuss it with me as well. And if you have any questions, I like a lot of interaction in the class, so please stop me and ask the questions. We'll try to clarify as we go along. Now, what is this course about? What do you expect to learn out of this? What does process control mean to you? Now, with me, from just intuitive point of view, obviously you have not taken the course. That's not a bad question. But what do you think process control is about? You've done process design is something. You've done an economics course, I guess, right? And so, and you've done material energy balance, so you'll be chemical engineers, chemical engineers very soon. So it is about controlling the process. So we are going to learn about, I will introduce today, basically I'm going to talk in general terms, introducing various concepts. But it is going to be a course that requires quite a bit of math. So we cannot afford to forget the differential equations that you have done. Laplace transforms, have you done that? Do you remember that? So we will review a little bit of Laplace transform. How about MATLAB? Have you done a MATLAB course? So you're comfortable with MATLAB? No? What is the reason for the difference?
use MathCAD, although I use MathCAD last semester.
Okay. All right, okay. I had this struggle in the previous university that I was teaching, and finally I convinced every faculty member to converge on MATLAB. So maybe I have a task not only in the class, that's outside. I mean, there are various tools, computing tools these days, and one can argue that if you learn one tool, it's very easy to learn another one. But practice makes it much easier. So if you practice just one language, you get better at that language. And I think MATLAB is the language for engineers and scientists. Very competing product of that. MathCAD is one, Maple is another one that's for symbolic computing. But MATLAB has a very good toolbox for control system design. So that's the reason MATLAB is adopted in all the control courses. But I've also taught courses on numerical methods where I teach MATLAB, and I've convinced my colleagues who also teach the same course to move away from Excel and use MATLAB. Because MATLAB, as you will find, I will, as you can tell, I'm a fan of MATLAB. So I will introduce a little bit, but there is so much to learn. What I know about MATLAB is probably only 10%. But I can learn as I need. There are so many toolboxes to solve in so many different areas that when I need to learn partial differential equations, I will learn about PDE toolbox. But in this course, we are going to learn mostly about control system design toolbox and maybe a little bit about signal processing toolbox. But we need to learn a little bit about MATLAB basic language itself. So if there is a need, I will set aside some tutorial time to take you through MATLAB introduction, and maybe I will also put some recorded demonstrations on MATLAB that you can work on in your home. MATLAB itself has nice simple videos that will tell you how to create variables, how to do matrix operations, and things like that. Simulink is an add-on to MATLAB, which is something like HYSYS. Have you used HYSYS, Aspen? So Simulink is like that. It's a block diagram-based environment where you just pull various blocks together and design a control system and look at how the control system will perform. So math is an important part, differential equations is an important part, and programming is an important part. And then everything that you have learned in chemical engineering courses. We are going to see process dynamics, models for process dynamics. So we will draw models from fluid mechanics, from heat transfer, from chemical reaction engineering. All those things will serve because the processes that we are going to control in a typical plant will have all of them, heat exchangers, pumps, reactors, distillation columns, and things like that. So we need to recall basically all those tools. So here is a kind of an expectation. What are the learning outcomes at the end of it? You should be able to use Laplace transform, use transfer functions, know what they are, use MATLAB to design control system and analyze the performance of a control system. So I will let you go through the outcomes. At the end of it, it will probably make sense, but I'm supposed to distribute at the beginning the rules for assessment and what you're expected to learn in this course. And the syllabus is also posted on Moodle. You can take a look at that. Let's just start a brief discussion about getting a feel for what control system is. Okay. What is process control? Here, what you have is an example of a shower. Okay, so you have cold water coming in through this tap with a control valve, a valve that we will normally, this is a very typical experience we all can relate to. So it introduces at the same time the terminologies that we use in process control. So you have one pipe that is taking cold water with a valve on its line, and another one bringing in hot water in this direction with a valve, and they are mixed, and the mixed water is dispensed through the shower head that you see here. Okay. So what are the variables? Obviously, you can talk about the flow rate, how much of cold water you are getting in through this, which you can control using the valve. Now, we also know about the temperature. It comes in at a temperature Tc. Can you control that? That depends on whatever the line temperature is. If you're taking cold water from the city supply, whatever the temperature that day happens to be is what you're going to get at. So that is not a manipulable variable. You cannot manipulate that. Okay. So we have identified the manipulated variable with this symbol, and the what you call unmanipulable variable as a disturbance variable. Okay? So these are the terminologies that we will be using in the course, so you should be aware of. So there is a disturbance variable that comes into the process, and the process itself is just a shower. Okay? And the same thing on the hot water side. You can control the flow rate, but the temperature is treated as a disturbance. You cannot control. That may not be true. If you have a hot water tank, you can go and set the temperature on that to some extent. But at the instant that I need, if I need to change the temperature, I need to wait. After I set the temperature, I need to wait for a while for the hot water, entire hot water temperature to change. So we're going to treat these as disturbance variables. So what is the control problem here? The control problem is to get a desired objective. The objective is I want water at a certain flow rate. I don't want trickling water. I want a decent flow rate. And I want it at a temperature that is comfortable to the body. Okay? So these are what we will call the control objective or set point. We are going to set the values for these variables. Now we can think of a distillation column in a refinery. Okay? So what would be the objective in a distillation column? Separation. So I'll give you a very specific problem. I have methanol water mixture. I'm feeding the methanol water mixture, and I have two products. The top product I want it to be pure methanol, and the bottom to be pure water, if possible. It would be possible to achieve in one distillation. So you would then specify the concentration of methanol that you want in the top stream and the concentration of water in the bottom stream as your objectives. And in the distillation column, then you'll need to manipulate the inlet flow rate, manipulate the temperature. Have you all done a course on distillation? I'm just using that as an example. Okay. So you have a reboiler. Okay, so you can adjust the reboiler duty to evaporate more methanol away and condense the heavier material, in this case water, in the condenser. So you have controls. Methanol, the cooling rate in the condenser and the heating rate in the reboiler. You can use that to meet that particular target. So there is a design process that you will go through to identify what are my targets and what would be the design criterion that will get me there. But what is the control problem in the distillation column? The control problem will be there may be a change in the feed composition. There may be a change in the flow rate. Okay? Or there may be a change in the ambient temperature. One day it cools down, so the distillation column is losing a lot of heat. Okay? So that would be a disturbance on the process. So a disturbance is anything that you cannot control, but that has an influence on the particular process. So you need to be able to manipulate your system in such a way that the disturbances are rejected, removed, so that you go back to your design condition, if you are operating at the design condition. So in this particular example, I have a certain flow rate and a certain temperature that I want, so I'm going to be able to manipulate the flow rate, the valve here, okay, to meet that particular objective. So this would be a manual control because I'm going and standing in front of the shower and adjusting the hot and the cold to get the desired temperature. But it gives me an idea of the terminology in terms of what is controlled variable and what is the objective. Okay, any questions? So at this stage, after this discussion, you have to tell me a definition for process control. What is process control? How would you describe it in your own words? Anybody want to try? I've hidden that part. I'll release it afterwards. But let's just think about it. If I have to, having discussed this particular example, I say on a piece of paper, give me your definition of what process control is. What are the key concepts that you will put in the definition? To maintain a certain set of conditions by manipulating certain variables for a particular process, that will be the process control. So it's intuitive. There's nothing that's magical about it. Okay. So the act of manipulating a certain inputs. So there are certain inputs to the process. You're going to manipulate the inputs in order to meet certain operational objectives, okay, certain goals, in the presence of disturbance. Okay, so there are disturbances, and you want to know what the disturbances are. Sometimes you may not know the disturbances, but you can know what the output is. So the output will have the influence of the input and the influence of the disturbance. So in the case of a distillation column, ambient temperature changes, that's going to affect the heat rate, it's going to affect the temperature in the cooler in the reboiler. But if you measure the temperature in the reboiler and the condenser, then you will essentially measure the effect of the disturbance. So the disturbance may not always be well characterized, known, but it is included in the measured variable. Okay? So using that measured variable, you can manipulate certain input variables to meet the objective. So that would be the kind of definition. Okay. So the operational objectives would be, in this particular example, we need to enjoy the shower, we need at a certain flow rate, we need at a certain temperature. Disturbances in this particular case, we already talked about it, temperature of the cold and hot streams. We cannot really control it, but we can control the outlet temperature by controlling the flow rate. Okay. The manipulated variable here are the flow rates. Okay. So we may operate the cold and hot water valves as per our fancy and meet the operational objective, even when there are disturbances in the project. Okay. So a few other terminologies. Sensor. What is a sensor? Something that measures. Okay. If you think about it, what is the perfect control system that you know? Air conditioner. Air conditioner. It controls the temperature. Now, I have lived in country that's very hot, and I've lived in country that's very cold. I originally come from India, but I've lived in Canada for 25 years. In India, we need only the air conditioner, okay? Because the lowest temperature that you get is only about 25 degrees. It's hot after that, okay? So you don't need a heater. But in Canada, it's the opposite. The highest temperature that I get is only 25 degrees, right? So we need a furnace, we need a heater, but we don't need an air conditioner. I moved to Baton Rouge only 6 months ago, and I need both of them. Very cold and very hot. So to condition the air, the atmosphere in a room, we need both a cooler and a heater. So you have a sensor. The sensor is right on the wall, the thermocouple. Okay? And you have a set point on the sensor itself. So you set it to 25 degrees, and it is sending a signal somewhere in the plant which sends regulated air through that. Okay? So you have a sensor, but what I had in mind when I asked that question, maybe somebody else has other examples of perfect control system that we didn't design. Nature, your body itself is a perfect control system. Okay? So you can look at the sensors there. We can sense through the eye, through the nose, through the touch. If a child, for example, touches a fire, okay, there is a whole process that intuitively somehow happens, and this is all can be broken down and explained in terms of this control language. So what happens? You have a child touching a flame. There is a sensor there. This can. The sensor is a heat, and immediately sends a signal instantly to the brain, to the nervous system. And the brain immediately sends a signal back through motor action to pull it back. Right? So here it is going through all the processes that we designed in the control system. There's a sensor which senses and sends a signal to a what we would call a comparator. Okay, so what we're going to introduce now is the concept of a feedback control system. Okay, what is a feedback control system? So you have a sensor that senses the information, sends a signal. In the case of a thermocouple, what is it? How does a thermocouple work? You know, you might have done it in a unit office. Right. So based on the temperature, it creates a potential difference. So you get a voltage signal. Okay. You can take that and using transducers convert it into anything else you want, but you can transmit the voltage signal itself directly. And then that signal has to be compared against what the set point is. So there is a comparator. Okay, the deviation is in this case, the deviation is the measured flow rate against the temperature. You need to know if I change the flow rate by a certain amount, how much is the temperature going to change. This is where we need the model. So process modeling is an important part of process control, particularly dynamic modeling, because we want to answer questions. To be able to answer questions like, if I make a change in the flow rate by a certain amount, how much is the temperature going to change? Not only is it how much is it going to change, how long it's going to take. And is there anything I can do to speed that up? These are all the issues that we are going to cover in this course. Okay. So the information on the process outputs, in this case the flow rate and temperature from coming out from the shower, is used to determine the process inputs. The output is measured and it is used to control the inputs, and that is what the feedback loop is. So again, conceptually we are talking about it. Pretty soon we will introduce in terms of a flow sheet diagram, a block diagram, identifying various elements. That's something that you should be able to do. If you're given a control flow sheet diagram, you should be able to identify what is the process, what is the sensor, where is the control element, what is the final control element, things like that. Typically in chemical processes, the final control element turns out to be some kind of a valve, because you're changing the flow rate often. But it could be a regulator, voltage regulator, outputting heat, for example. If you have an electrical heater, you just change the regulator voltage and the current, and you can produce the heat directly. But often it is simply the valve. So the next question one can ask is, why do we need automatic process control? Okay. So here is a scenario. The disturbances is occurring very frequently. Okay, the temperature of the hot water and cold water, I don't know whether it happens in your dorms, but sometimes if somebody else opens the hot water and you're having a shower, the water supply is changed on you all of a sudden, right? So you immediately need to go and change the flow rate. So imagine that kind of a situation where you don't have control over the disturbances and it is changing very frequently. Okay? So it would be nice if, instead of me manually adjusting it every time, I have a sensor and I have automated the whole process, and I have a thermocouple at the outlet of the shower which sends the signal back, and it automatically adjusts the temperature, the flow rate of the two streams, bringing it back to the design point. Okay? So the automation has helped the chemical industry tremendously in terms of not only cutting the manpower, but keeping the product quality, sort of re-observing and going and changing. In the 30s and 40s, you will have in chemical plants a lot of operators who will actually manually change the valve to maintain the quality. But nowadays it's all automated, and so automatic process control can respond much quickly, can maintain a tighter specification on the outlet that you want. And there are other issues like safety and the experience of the operator itself, why we need automatic process control. So here is an example. If a 7-year-old is having a shower, is that person able to control it as well as an adult would be able to do? Okay. So again, an automatic control where you just set the temperature of the shower and you just walk in would be much better than asking a 7-year-old to adjust the valve. And the other extreme would be an elderly person who cannot respond very quickly to changes, can get burnt, scalding, because of high temperature. Right? So again, automatic control in those scenarios would help, and there are two issues then. One is safety, the other one is product quality. Okay, in chemical plants, you can maintain higher quality, and when the process drifts towards extremes, you can shut down. You can program it in such a way that the process will be shut down. Now, even in this example of the shower, you can ask the following question. Think through this following scenario. Okay. Typically, you have, say, the hot water available at 80 degrees, cold water at 40 degrees, and cold water say at 25 degrees, and you're getting the water at 36 degrees. All of a sudden, the cold water that is available jumps to 40 degrees. So what is the coldest temperature that you can get? 40, right? No matter how much you shut down the hot water, you cannot bring it below. Okay? So there are limits. What this points out is there are limits to operation, and you need to build into your control system procedure for shutting down when safety is at question. If your process has taken excursion to extreme limits, then the temperature in a reactor, for example, it's an exothermic reaction and it's becoming hotter and hotter. You need to say, if the temperature exceeds a certain limit, shut down the process. Okay? So safety is also a consideration that we need to build into our processes. So this is the example I was talking about. Assume that the hot water steam temperature increases from normal 50 to 80, and the cold water temperature increases from the normal 25 to 45. Okay? So let's assume that the shower temperature increases from 38 to 67 as a result. The control system will try to negotiate the disturbances, decreasing the flow rate of the hot water, but it cannot meet the criterion. Then we need a safe way to shut it down. So we must have an abnormal situation handling system. Typically, these are safety valves that will, safety procedures that will shut down the system, bring it down in a safe manner. So such safety systems can be embedded and should be embedded into the design of our control system. Okay, any questions? So the next point is that even if you have designed the control system very carefully, you cannot use the control system alone to meet your objective. Okay? So the control system is built on a design. So there are optimal design criterion, and then there are limitations on the design, okay, upper and lower bound, beyond which you cannot operate a particular process. Okay? So if you're trying to solve a design problem with control, that's not going to work. So you need to have control only to set limits for safety or considerations, but you cannot use control to improve your design. The design has to occur first. Once the design is complete, then you take that and build a control system on that, putting extreme limits at which the design itself will fail, and so you need to bring the system down in a safe manner. So in this particular case, you cannot ask for a temperature that is above the incoming hot temperature or a temperature below the incoming cold water temperature. Those sets the design limits. And if you need to address that issue, if there is an issue, then you need to go and redesign your cold water and hot water supply systems. So basic lesson here is no super operator or no advanced control system, no matter how sophisticated it is, can overcome the limitations of a poorly designed process. So design comes first, and control comes on top of that. We have a number of other examples that we're just going to go through to reinforce this idea of what is a sensor, what is a control element, in different examples. So here we are driving a car. Okay? The objective is to go from point A to point B safely in a reasonable amount of time. So what are the sensors? What are you sensing all the time? In meeting the objective of going from point A to point B, you obviously want to know where you are, because you need to know where you are getting to. So these days GPS helps you, but otherwise you would typically look at the surroundings, you have to have a map, and you'll be guiding yourself along the path. Okay? So the position of the automobile and the speed, because you want to get there in a certain amount of time. You want to get from point A to point B in a certain amount of time. Okay? So the sensors would be your location and your local speed that you would want to observe. What are the disturbances in this case? Traffic is a major unpredictable disturbance, and the road conditions, the bumps, and changing speed limits. If you don't know that you have to go through a region where the speed limit is lower and you underestimated your time, for example, could be a disturbance. So the manipulated variable would be your foot on the pedal, right? So you can accelerate, you can brake. These are the control variables, the manipulated variables that you can use to get you to the target, okay, in the presence of disturbances. As you talked about controlling the air conditioning, here is an example. Now we are putting some figures, some structure to this. Okay, so heating a room by circulating hot water through a pipe. Okay, so objective is to maintain room temperature within a desired limit. What is the sensor? The sensor is the thermocouple on the wall, the temperature measurement device. Disturbances would be heat losses, heat gain through the door opening, window opening, general heat loss through windows, etc. Okay? So the manipulated variable is the amount of, in this case it's a heater, so the amount of fuel that I need to burn to produce the hot air to be pumped back into this room. So we can put all these into a structure like this, a block diagram. This is what we'll be doing in this course, simply representing each element, a control unit, a measurement unit in terms of blocks, and then putting an equation to each block. What does that particular element do? If you think about the thermocouple, if you have to describe, as you said, what happens is you have a bimetallic tip that produces an electrical voltage in the presence of a temperature. But it has its own dynamics, meaning if I take a thermocouple and put it into hot water, I'm going to get a voltage signal. Is that voltage signal going to be instantly representing the temperature of the water, or is there a time delay? Okay. So if a thermocouple is actually very good in terms of the time delay being microseconds. But if I take a normal thermometer that the doctor uses to measure the temperature, he doesn't insert it and take it out immediately, right? He has to leave it there because the mercury has to expand. It has to be heated up, it has to expand. So each time constant, the time it takes for it to reach its final state would be of the order of 30, 40 seconds, up to a minute or so. Okay? So each of these process elements that we're going to talk about, whether it's a measuring element, whether it's a valve. When I close the valve, for example, do I close the valve instantly, or does it take certain time? Okay? So there is a time that dynamics involved in each one of these process units. So we need to write down the model equations for each one of those, not only the process, but the control element, the measuring element, all these, and how do they interact dynamically so that we can get an idea of what would be the dynamic response the moment I make a change. So here, what you're seeing is a block diagram representation of everything that we're talking about. We have a room, we have a sensor, which is a thermocouple, sensor signal. And there is a set point. Typically, in the case of thermostat, the set point is over there. So the comparator is an element like this. The plus minus signal simply says that I'm taking the difference between these two signals. So if I'm setting it at 25, I mean the temperature is 28 degrees, and I'm setting it at 25 degrees, I have a 3 degree difference. And that difference is the one that is sent to the controller. The control element in this case is actually in a different room. Okay? So the controller receives the signal and says there is an error between my goal, my objective, and what is actually being there in that room. Okay? So it generates, so it needs to get a quantitative information. How big is that difference? Is it 3 degrees, is it 5 degrees? Because it needs to calculate how much of hot air I need to put into this room. Okay? So that is a mathematical algorithm here, the rule that we are going to design. So much of the course is going to be looking at how do I build these controllers. Okay? So that it gets an error signal and it sends out through that a control action signal. Okay? So these signals, it could be voltage coming in there, and what comes out is so many BTUs per hour. Okay? So the controller figures out if I get a voltage of 5 millivolts, that means it corresponds to a temperature of 3 degrees, and it does the calculation using the process model, and it says, okay, I need to send 500 BTU per hour to bring back the temperature by that 3 degrees. So that action goes to a control valve. Okay, that means you need to increase the fuel rate. You need to burn more fuel. Okay, so that also will have its own dynamics. And then the fuel goes into the furnace, and then you have, in this case, it's a hot water loop. So the hot water temperature goes up, and the heat is delivered to the room. That completes the cycle. So this is why it's called a feedback loop. Okay, so you are measuring the current patterns and using a model, knowing what the difference is, predicting what the required duty is, and sending it back and bring it. Now, if you wait for a few minutes, you will find that the error goes down. When the error goes down and the set point is the same as the measured temperature, the signal is bigger. And that means it shuts off the okay? So it is putting together, integrating what happens in the process. In this case, what is the process? Let me ask you. let's go through this idea of identifying what are the various elements. What is the process that I'm trying to control? Temperature in the room. This is my desired objective. Right? So my focus is on this particular thing. This could be replaced by a distillation column, it could be replaced by a reactor. Okay? But in this case, this is the process. So I'm sensing something about the process. Okay? And then I'm building a control loop around it to bring the process back to where I want. So the sensing element, of course, is control. Okay? And what is the final control element? That actually does something to the amount of fuel, but the element itself would be the valve that controls the fuel. Okay? So it's a physical device. The final control element is typically a physical device that creates an action. Okay? In this case, it lets more fuel flow through to the furnace, and then you have on one of these produces. Can you think of other ways of operating this? One of the other variables that can affect the room temperature. Let me ask you, you're going to heat transfer force, right? That's the rate of heat transfer from this to the room, depends on anything about the loop. The speed at which the water is flowing and the surface area of the heater there. Okay? So a design change, for example, if you want to put in down to minus 10 degrees in Baton Rouge, right? So you need to put in more heat and it's not able to deliver. Okay, you try increasing you can burn all the fuel that you want there, but if it's not able to transfer it to this place, it's not functioning. Okay? That would be an example of a design limitation in your heater in the room. Okay, so this is a kind of a water heater with the radiant on here. So you need to say this is not enough, so I need to increase the area. You can try increasing the flow rate. That doesn't work. You can try increasing the area. Any questions? Basically reviewing components of a feedback control system. Okay, so the process is the centerpiece. That is what we want to control, and the sensor is an important part of the feedback loop because that assesses the current state of the particular system. Then there is a comparator which compares the set point. The set point sets the objective. Okay, and the sensor signal minus the set point gives you the error signal. So E here stands for the error signal. This is the set point, and this is the present value of the process variable. Okay? And the controller then takes that error signal and produces an output, a controller output, which goes to the final control element and actually causes the control action to take place. We talked about the controller can be a human operator. This is how it was earlier, but nowadays we have automatic feedback control system. Okay, so the control algorithm, we're going to talk about what are the ways in which the controller, because the whole course is going to be actually about point 3. How do we take a control action based on an error? What is the error? The error is the difference between exactly. Okay, I think that noise is it bothering you guys? Okay, so the error is the difference between the set point and what the sensor puts out. And so, for example, if the error is positive, you can say, I'm going to turn the furnace off, let the fuel flow. If it is negative, I'm going to shut off the fuel. So this would be called an on-off controller. Okay, so you're really not controlling the amount of fuel. You're just saying, I'm going to always use a certain number of fuel, but I'm going to regulate for how long the furnace is on, how long it is off. And this is called on-off control, the most primitive controller that you can think of. Okay? But it will get you the job done, but it will take a longer time because it's normally going to overshoot. Okay, so what will happen is, for example, the room temperature is 25 and you want it to raise it to 28, it gives the furnace off, puts in a lot of heat. Okay, so the room temperature goes from 25 to 26, it goes on 28, 29, and then it says, okay, that's exceeded, it shuts off. Okay, and then it starts going down, so it will just be hovering around the set point. It never reaches the set point very well. Okay, so that's the on-off control. The more sophisticated control would be one where you say the controller output is proportional to the error. KC is called the proportional constant. Okay? So if the error is 2%, then the controller action will be calculated based on that. Of course, you are, as a designer, supposed to tune the controller constant. What should be that? This is called the gain. So 1% error, how much fuel should I burn? 2% error, how much fuel should I burn? You need to figure that out. Okay? Once you have the model, you'll be able to figure that out. Okay? And the next one is called the integral controller. Here the controller action is not only proportional to, there is always a proportional part, but integral, I think there is actually an error there. There should be an integral sign. Okay? Integral of the error. Okay? Why is that important? Why could that be important? So in the second case, we are saying that the controller output, the controller decision depends only on the current error. Okay? So if you plot, for example, time, and this is a set point. Say the temperature is 25 degrees, and this is actual temperature. Initially the temperature was 23 degrees, it is going towards 25 degrees. So what will be the error? The error will be the difference. Okay? So the proportional controller says the amount of fuel that I'm going to burn at any instant of time is simply proportional to this vertical distance, the error. So as the error becomes smaller and smaller, the valve is going to gradually shut down a little bit more, until when it reaches 25 degrees, the valve is completely shut. Okay, so that's what a proportional controller does. What does a proportional integral controller do? It takes the integral of the error. Okay, so it takes how much was the error before, what is the error now, what is the error the next time step, integrates them. And then develops a control action based on that. So what do you think, why would you think you would need something like that? Why did somebody think of it? It minimizes the overshoot, and it also minimizes something called an offset. For example, you might have a situation, and we will see later on in the example, through a specific example, that the temperature never reaches 25 degrees. You set to 25 degrees, and you're burning at a certain rate, but there are losses along the way as the hot air is coming into this room. Okay, so it never reaches. The proportional controller can get into a situation where it never reaches the complete set point. So there is always an error. Okay, so an integral action will say that recognize that the error is constant. So I integrate that error, and then I compensate for it. Okay, so it prevents things like overshoot or undershoot. Okay, and allows you to reach the target. The other one is, which is not here, is called the derivative action, which says how fast is the error changing. One is what is the current error, that is the proportional controller. The second is what is the accumulated error over a period of time, that's the integral action. The third one is the derivative action, which says how fast is the error changing now. Okay, not only what is the error, but how fast is it changing. Okay, so based on that, I can predict, anticipate how it's going to go, how the process is going to go in the future, and adjust that. So the best controller, and most widely used in industry today, is called a PID controller, proportional integral derivative controller. Okay, so this controller will have three constants that you need to tune: the proportional action, the extent of the integral action, extent of the derivative action. With that, you can bring most of the controller not only to the final state, but in the most rapid response time. You don't take forever to reach the final state. Once you change the set point, you want the process to reach the set point as quickly as possible. So it gives you enough freedom to control not only the set point, but how fast you reach the set point. Okay, so you should know a basic idea of what the PID control means, proportional integral derivative, conceptually at this stage. Any questions on that? You guys are very quiet. You must have some questions. Okay. Sensors are, as we talked about, one of the most crucial components of the feedback control system. If the sensor fails, you cannot control it. Because if the final control element fails, you cannot control it either. Okay? So all of them put together makes the control loop. Final control element, we already talked about it, valve being the most typical one. Besides these sensors, the final control element, and the controller itself, which is the heart, the brain of the system, we have a lot of other systems that can be part of this entire loop that we talked about. One are called transducers. What do transducers do? They change the signal from one to the other. Okay, so you can have a signal coming in as millivolts, and you want to convert that into so many psi pressure. Okay, because how do you control the valves? Typically, the valves will be controlled using a pressure. Okay, so you need mechanical motion for controlling the valve, whereas the thermocouple is putting an electrical signal. So you need a transducer that converts an electrical signal to a mechanical signal. And multiplexers are basically wires or media that carry multiple signals in the same wire. Okay, and terms like E to P, I to P basically stands for voltage to pressure or current to pressure. Transducers that will convert a voltage signal to a pressure signal or a current signal to a pressure signal. So let's just briefly wrap up what we've seen today. Why our process is controlled, of course, to meet certain safety objectives, to meet certain product quality objectives, to meet profitability objectives as well. If you produce the most pure product, you get the highest reward for that. And safety is an important reason for controlling the plants. Minimize the operating cost, consistent product quality, smooth operation, and safety. Safety is on the top. What is this diagram? This is a typical strip chart that you will notice in older chemical plants. These days, in newer ones, the same information comes to you on a screen. Okay, but what is this? This is simply measured output from a sensor. Okay, so it could be a thermocouple or it could be a pressure sensor. So you have in the early part, up to this part, you have a signal coming in from a process. And what we have done is we have put some control action. So this is without any control action. There are fluctuations in the process. The moment you put the control action, you notice, what do you notice there? The error in the process deviation from the set point. The set point would be like 96, for example. You want to operate it at 96. So without the control action, the product quality could be, like if it's methanol concentration, you want to operate at 96% purity, it could be 94, it could be 98. Okay, because of the disturbances on the plant. It could be fluctuating wildly. By putting a control action, you are able to narrow down, you are able to improve the product quality. And what has happened at this point? You change the set point from 96 to 98. Okay? So there is a dynamics involved. That's what this one shows. It doesn't reach instantly. You change the set point instantly, but it doesn't reach, the process doesn't reach the set point instantly. It takes a certain amount of time. By manipulating well the proportional integral derivative action, you should be able to minimize this. You may be able to take it like that. Okay? So that's what the controller design is about. So what you see in the bottom one are so-called histograms, which tells you what is the distribution, how widely the product is distributed. So here, the standard deviation is quite high, whereas you're able to bring it down from 95.5 to 96.5. Previously, it was 94 to 98. Okay, so you're able to bring down the variability in the product quality. And this is simply changing the set point from 96 to 99. So another way of saying that is set point tracking and minimizing the variability in the product quality is an important objective. I think we are probably running out of time. So I will continue from this point on, and the next lecture will be on the model. And we'll see you on Friday.
Yeah.